Hello everyone, this is the fifth lecture of our course EEE 4483. In this lecture we will try to understand the details of analog to digital and digital to analog converters, and most of the contents for this lecture I took from this book, so you can go through that if you want. So let us start. First of all, let us try to understand what is the difference between analog and digital signal. So in the left, the signal you see, this is an analog signal, and in this signal the horizontal direction is denoting the time and vertical direction is the amplitude, and in both of the direction you can see the signal has continuous value. This is not discrete. That means within the range in vertical direction or horizontal direction it can have infinite possible values, right? And whenever we are talking about digital signal, what we do, we try to quantize or discretize for both of the directions. I mean, we try to discretize the time domain as well as the amplitude values are discretized for the case of digital signal. So how does that happen? Briefly, initially we will try to discuss that, how that happens through this picture. So what we do, as I said, we have to quantize or discretize both of the axes. So first of all, let us start with time. What we are doing here, through a process we will try to quantize the time direction such that after some time interval, a finite time interval, we will sample the voltage we have, the amplitude we have of our signal, of our analog signal. So you see, after this amount of duration we are taking a sample of the signal. In this way, after going through the process, we have discretized the time domain, right? And this is what we call sampling. So after sampling, what happens, still the vertical direction or the amplitude domain is still continuous. We have continuous values here. The problem with this kind of signal is that why we try to convert any analog signal to its digital version is because of the devices we have. The devices we use for any kind of communication or information passing, these are digital devices, and we have finite amount of storage, right? So what we do, we try to quantize or discretize these values, the signals, so that we can within our storage or mechanism we have in digital devices, we can transmit the signal properly without losing much information. So you see, because we are losing some information here in the time direction, still what we will see, the signal we are getting after this process is quite resembling the original signal without losing much of its information, right? So now we have talked about sampling, right? After that, what happens, the amplitude portion is still continuous, so we will try to quantize that through a process called quantization. So how that happens, you can see in this graph what we have done. The minimum voltage for the analog signal was 0 voltage and the maximum was 10 voltage, right? So we will try to divide this whole voltage levels from minimum to maximum into some states. So we have how many? 1 2 3 4 5 6 7 8. So we have divided into 8 different portions, and each of them has a length in the vertical direction of 1.25 volt. Okay, so what we are going to do, we are going to take these particular states, and whenever a sample signal resides between these particular states, we will take that as a particular state. So we have quantized states instead of the continuous state. So each of the signals we have in sampled signal, all of them will obviously reside or fall between any one of the states we have here. So instead of this continuous value, we have only 8 possible combinations for amplitude now. So this is called quantization. Then what we do, because our digital systems only understand 2 possible states, 1 and 0, or you can say 5 volt or 0 volt. So what we will try to do, we will convert or encode those quantized values into a digital value, a binary value, right? So that's why what we are doing here, we have 8 states. You know that because we have 8 different states, to represent them properly we need at least 3 bits, right? So because we have something like 2 to the power 3 is equal to 8. We will discuss about that later on, but just try to understand that because of that we have used 3-bit values for each of the states to represent them, and we have actually assigned 3-bit values for each of the states starting from 000 up to 111, right? So now what we'll do, for each of the sampled values we have or sample signals we have, we will have a specific 3-bit output, right? Like for the case of this particular state, which is starting from 3.75 volt to 5 volt, for this particular case we have assigned the binary value of 011. So that means after this signal, after encoding, we are going to get 011. So in this way, for each of the sampled signal we are getting 3-bit values, and this is the final digital signal we will transmit through our digital device, right? So this is the digital signal compared to this analog signal. So what we have done, we have converted this signal that is continuous in time direction as well as amplitude direction into a signal that is only 5 volt or 0 volt, right? So sequentially we can send this signal and our system will understand that this is the signal we have transmitted without losing much of its information. Okay. So that is what is discussed here. So analog signals are basically continuous in both time and amplitude. They can take any value within a given range, right? So infinite values are possible. And for the digital signal, we are discretizing both of the domains, right? So we are discretizing time and then amplitude, and because of that we have only specific finite values, and it will reduce the amount of storage needed for our system whenever we are trying to transmit the signal, right? And now let us try to understand what are the limitations of analog signal, why we are trying to convert everything into its digital version. Because you know, analog signals can pick up noise as they are being amplified, obviously, because they are continuous. Because of any kind of noise, they can pick up noise, and that will attenuate or fluctuate the analog signals we have, right? Because infinite values are possible, right? And obviously analog signals are difficult to store because of this situation, right? Because we have infinite possible values in both of the directions. To store them we need huge amount of space or storage, right? And that's why they are very expensive. Compared to that, digital systems obviously are much efficient, because all of the signals can be converted into only 2 possible states, zeros and ones. So even if some noises are there, we know, like when we talked about logic levels, how concept of logic level can eliminate the issue of noises. So that's why we will say even after getting some kind of noises in our system, it can tolerate that, and we are going to get the signal we want in digital domain, right? So obviously another thing I discussed earlier, it can be easily stored in the memory, because now the number of possible states are reduced compared to the continuous time and continuous amplitude version of the signal. And because we have opted to digital domain for a long time, so we will see that now we have systems, digital systems and fabrication mechanisms that has become quite more advanced and less costly compared to the analog signal devices. So that's why we always try to transmit or generate digital signals for our devices, right? One of the major limitation of our digital system is that, obviously, if you look at the previous graph here, whenever we are talking about the continuous signal, the analog signal, it is the accurate representation of the signal. Whenever we are trying to sample it, we are losing some information here. When we are trying to quantize that, we are losing some information in amplitude domain, right? So because of that, obviously we are going to lose some information, but we have to be careful that the interval we have for sampling and also the number of quantized state we have, that should be high enough so that we are not losing valuable or much information from our analog signal, right? But this is one of the limitations of digital systems, we can say. We cannot definitely confidently 100% convert the analog signal into its digital version. There will be some losses. Okay, now whatever we have discussed earlier, this is in a graphical manner explained here. So we have this analog signal. After the sampling, you see in the time direction we have discretized the signal. We have the samples after some finite durations, right? Then we will quantize, that will divide our overall voltage domain into some states, and that will could discretize the amplitude or vertical axis, and then for each of the states we will assign some binary values, which is called encoding, right? After encoding, the digital data we have got, that will be transmitted, right? Then as we have briefly learned about all of the steps that relates to the analog to digital conversion, now let us look into the details of each of the cases, right? So let us first start with sampling. So sampling is basically the process of converting an analog signal, which is continuous in both time and amplitude, right, into a discrete time signal, which is discrete in time but still continuous in amplitude, right? So as you can see, we have a sampling interval called Ts, and after each sampling interval we are sampling the signal. So this is actually discretizing our time domain, but still the amplitude value is continuous. But you'll see that we will discuss that this value of Ts or time interval, sampling interval, should be carefully chosen, because there will be a problem called that relates to Nyquist sampling theorem. So let us discuss about that. So maybe from your previous semester you have learned about this particular problem. So whenever we are trying to sample any analog signal, the sampling frequency of that sampler should be at least twice of the highest frequency present in the analog signal. So what does that mean? In our analog signal there can be different frequency component. There can be high frequency component, there can be low frequency component, but we are talking about the highest possible frequency present in the analog signal. And if we want to sample that, our sampling frequency of the sampler should be at least twice of that or higher than that, right? So if the analog signal is g of t, which has frequency, the highest frequency component of that is fm, then to reconstruct that gt from its sample, the sampling frequency fs must satisfy that fs is greater than or equal to 2fm, right? So the minimum sampling frequency, which is equal to 2fm, is called the Nyquist rate, right? So we have to take at least twice or greater than that for proper sampling, and reciprocal of that will be called Nyquist interval. So what problem happens, let us discuss about that. If we don't take a sampling frequency that is not at least twice or higher than the maximum frequency component of the original signal, then there will be issue called aliasing that will happen. So what happens, let us try to understand that. So in aliasing, what happens, the spectral components of the signals overlap in the frequency domain. So it will cause higher frequency components to be misinterpreted as lower frequency components. So whenever we have a sampling frequency that is not enough, that will, for the higher frequency, it will cause some problem. It will be interpreted as lower frequency. We can understand that if we look into our signal in frequency domain. We are not going to do that, but using this graph maybe we can still try to understand. You see the blue graph you can see here, this is the original signal, the analog signal we want to sample, and for that the samples we have taken are these things, the red dots you can see here, with some value of TS, the sampling frequency, sampling period, right? So we can obviously understand that the sampling frequency we have taken for this case is not adequate enough, because the frequency of the original signal, the sampling frequency should be at least twice of that. It is not twice of that, it is even less than the original signal. So as a result, you see, when we are trying to reconstruct the original signal from those samples, we are getting some misinterpreted signal. So here you can see this is the interpreted signal from the samples, and the frequency of that is quite low compared to the original blue signal. So that is the problem. This is called aliasing. Okay. If we understand that, now let us look at the practical circuits, how we do sampling in analog signals. So the circuit we use is called sample and hold circuit. We understand about sampling, but why we have this hold portion here? That is the question, right? So the problem is, you know that whenever we are talking about analog to digital conversion, there are different steps involved. First of all, we have to do the sampling, then we have to do quantization, then we have to do encoding, and all of the processes take some time, right? It will take some time. So previously, in the previous cases, in the graphs we have seen, like if I want to show you, like here, here in this very momentary duration, we have just sampled one value here, right? But if we try to do the whole process, sampling, then quantization, and then encoding, obviously it should take some time, right? It will need some time. As a result, if I just momentarily take the sample and then do not hold that value for some duration, the whole conversion process, whole analog to digital conversion process cannot actually be done, right? So as a result, what we do, after we sample, we hold that value for some time, like that, okay? And this is actually are being done using your sample and hold circuit. So let us try to understand that. So you see here, we have this analog signal, right? And we will try to sample and hold that signal. So how to do that? So you see, we have this circuit here, right? We have this circuit, and using this circuit we will try to do this sample and hold process. And here you see, this is the output signal. So here you can see, in this initial portion, the output signal is exactly following the input signal. Then at this moment, at this portion, we try to sample our original signal, right? At this portion we try to sample our signal, and after that, for some finite duration, we will try to hold that value through capacitor or something, so that in this duration, in this particular duration, we can complete our overall analog to digital conversion process, right? And then again we will for some time follow the input signal, and at this moment nothing will happen, no conversion will happen. Then again, after that TS sampling period, the duration we have to wait for each sampling, then again we will sample here and hold that value for some duration. So in this way this thing happens, right? Now this is what happens, and how this happens is through this circuit. So this is the input signal coming from this signal, and we will have a switch which we can control to close this circuit or open this circuit, and through VC we will get the output, and there will be a capacitor connected across our VC voltage. So what happens whenever this switch is closed like that, right? Switch is closed like that, at this moment this particular thing will happen. Let me remove everything so it will be easier to understand. Okay, so whenever this is closed, okay, whenever this is closed, we will see that the output voltage is actually following the input voltage, which is we are calling track mode. Okay, so the output is just tracking the input. Then whenever then maybe we can open this switch, and then this value, whatever signal we have stored through this capacitor, because whenever we were closed, we were getting the output VC, because this path is closed, but at the same time this capacitor was getting charged, and whatever voltage it was holding, it should be kept here whenever we open this switch, right? So we have opened this switch. Now what will happen, whatever voltage we have stored at the last moment, that will be stored here until we close the switch again, and this is what we are calling the hold mode. Sample, then hold. For this duration we will hold. Then again, after the whole ADC process is done, what we will do, again we will close this switch. Okay, so we will again close this switch, and again we will see that this kind of situation is happening. We are just following or tracking the input, and at the same time the capacitor will get charged to hold that voltage, to keep that voltage, and then again we will come here, the switch will again be opened, and capacitor will hold its last voltage, and we are going to see this situation where we are holding the voltage we have sampled for some duration. So this is the whole sample and hold process. So now let us try to understand practically in this type of circuit what problems may happen, and what modifications we can do to alleviate those problems. So whenever we are talking about the sample and hold circuit, just like before, there should be a switch here, right? And there should be a capacitor here through ground, and this is the output, right? Now whenever we are talking about the input voltage, we know that all of the voltage sources we have should or generally have some amount of internal resistance here. So let us represent that using this resistor here, and this is our voltage source, the input analog signal we are providing, right? So let us call that Vs, and the internal resistance of that is Rs, right? This is our switch S, and this is the capacitor. And also whenever we are talking about the output, generally some devices will be connected, like quantization and encoding devices, that will be connected here in this portion. So we can represent any kind of devices like that as a load. So load means there will be some resistance, right? So we can represent that like that, so with a resistor here through the ground, and let us call that RL, right? And finally that will be going as the output, right? The output of our sample and hold circuit. Now the issue is, we know that this capacitor which is getting charged here and sometime is getting trying to hold that voltage for that duration. So this capacitor takes some time to get charged, and also it has some issue that it can get discharged whenever it is trying to hold that voltage. So let us discuss about the first case, whenever we are charging that, right? So whenever we are charging that, then this switch will basically be closed like that, right? Something like that. And whenever this switch is closed, the current will go in this path for this capacitor to get charged in this tracking mode, right? In this tracking mode. Now we know that the capacitor takes some time to get charged. So how much time it takes is dependent upon the RC constant, right? So charging time is related to tau, which is the RC constant. In our case, because in this path this is getting charged, the value should be Rs multiplied with C. Okay, and generally if you want to exactly know what is the amount of time for it to get fully charged, the value should be 5 tau. Okay, approximately 5 tau. So we can understand that this is the value that governs the amount of time this capacitor will take to get charged. So if that is the case, ideally what we want, in this case we want this capacitor to get charged instantaneously without taking any delay, because we want to follow or track the input voltage exactly like the input voltage without any kind of lag or delay. If that is the case, ideally the time taken for it to get charged should be 0, right? It should instantaneously get charged. So ideally the value of this RS should be as low as possible, but we know there will be some finite value of resistance here as RS, which is coming because of Vs, and we need to eliminate that somehow so that this value is as low as possible, and we will see the tau value will be very low and capacitor will get instantaneously charged to get this kind of behavior in tracking mode, right? Now let us talk about let us just say that we want this RS value, the input resistance, to be as low as possible, and for the case of discharging or holding, actually whenever the switch is actually open, right? So let us try to discuss that. So whenever the switch is opened, at that moment whatever voltage we have stored in this capacitor, that will be hold, or it can also get discharged, because through this path there will be some current flowing, and because of that current flow there this voltage across this capacitor, let us call that VC, will keep reducing as the time progresses, right, in this duration. So we can calculate that the time taken for it to get discharged is related with this tau value. Let us call that tau 1 and let us call that tau 2. So tau 2 is equal to RL multiplied with C. Now here ideally what we want the value of this to be as high as possible, because then what will happen, then this value will be very high, and if the value of tau is high, that means this capacitor will take more time to get charged and it can hold the voltage it has, right? So basically if you have higher resistance here, the current flowing through this path will be less, that means less amount of current flow means less amount of voltage drop here, right, which we want ideally. So ideally what we want, this RL value to be as high as possible, but generally we know load means load necessarily does not have high amount of resistance. It can be any value, but if it is low, that will cause some problem. So these are the two problems we have. We need to have RS to be as low as possible, RL to be as high as possible. So how can we resolve that problem? If we build a circuit practically, how can we resolve that problem? So to resolve that, what we are going to do, we are going to modify this circuit such that there will be an op amp like this, okay? And the configuration we have is called buffer. In this configuration, we know that whatever input voltage we have provided through the positive pin, that should come out at the output, right? So whatever we are providing, we are getting the same thing. But what benefit we are getting from that? The benefit is that we know whenever we learned about op amp has a characteristic such that the input impedance of the two pins are quite high, theoretically almost like infinite, or practically it is very high, right, very high, and the output impedance of the op amp is quite low. So this is the behavior what we want to utilize in this circuit. So because you know in this circuit whenever the switch is closed like that, in this particular case the capacitor is connected with the output of the op amp, and in this configuration if I look through this path, the op amp has quite low impedance. The effective impedance of this particular portion for the capacitor is quite low, which we want, right? So the effective tau or RC constant will be quite low in this case, and we will see that the capacitor now can get instantaneously charged because the effective resistance or impedance, we can say, is quite low for this case. And for the issue of the output, what we can do, we can modify the circuit such that here also we are going to have another buffer. So here we are going to connect another op-amp buffer like that. So now for this buffer, because the input pins of the buffers are connected with the capacitor, whenever we are in discharging or holding situation, what will happen? The capacitor is seeing the op-amp or the output as the op-amp input, which has a very high input impedance, right? Impedance. So because of that, for this path, the effective resistance or impedance and multiplied with this capacitance should have a high value, very high value, right? So the RC constant will be quite high. Because of that, the discharging time for this capacitor will be very high, and we will say ideally the capacitor will not get discharged that much within this duration, the duration we need to hold the voltage across our capacitor so that we get the output, right? So this is the modified circuit, this is the improved circuit for these two issues we had, right? And you will see that this is the final circuit. And what we do, because we cannot manually control the switch on and off to get this kind of behavior, you see we have to use this kind of behavior, so that some of the portions we are tracking the input voltage, and for some of the duration we are holding the voltage. So we have to close this path for tracking mode and open this path whenever we are holding the voltage, right? And how does that happen? Using this kind of MOSFET. So here we have an n-channel MOSFET, and through some control signal like this, a square pulse like that, for some of the portion we will have a positive voltage, maybe 5 volt or something, and for some of the duration we will have 0 voltage. So whenever we will have high or positive voltage as control signal going to the gate, it will turn on the switch and close this path, and whenever we have 0 voltage like that, it will just turn off this switch and this path will be open. So in this way we will control this particular path, right? Now let us look at some of the parameters we have for our sample and hold circuit. So in this figure we can see actually in practical input and output how the wave shapes can behave. So the graph with prominent black line, this is actually the input signal, and this portion is actually the output signal after sample and hold. So basically what happens, you see whenever you are actually switching the circuit so that the MOSFET is turned off and the path is opened, and whatever voltage we have sampled, that should be hold for some duration. So you see at this line here we have actually given the pulse through our square wave, right, through the gate for our MOSFET. And because our device or our MOSFET takes some time to respond and to open the switch, this duration is actually here. So you see, even though we have given the signal to turn off in this particular time, it has responded after some time, and after that we have seen the holding stage has started. So for this duration the output was following the input, and after that you see the output voltage is actually holding the voltage, and you see, so this is actually called the aperture time. Okay, so the time interval between the control signals command to enter hold mode and the instant when the input signal is effectively disconnected from the hold capacitor, right? So basically delay for the switch to open. So we have given the signal and switch has actually responded. So this is the gap between them, the time gap. This is called aperture time. And similar thing also happens for the case whenever we are turning on the switch. Turning on the switch means we are closing the path so that again we can follow or track the input voltage. So from here to here, you see we have actually turned on the MOSFET switch so that now the output can follow the input. But because we are talking about capacitor, and capacitor will take some time to get charged to its voltage equal to the input voltage. So this amount of time taken, you see through the wave shape you can understand it is taking some time to get there, to reach there. This is the time which is called acquisition time. Okay, and finally droop rate. the rate of change of the output voltage whenever the circuit is in hold mode, because you know nothing is ideal. So even the capacitor has some leakage current, because of that the voltage can drop, and this is actually this droop, right? So droop rate is basically the rate of change of that output voltage. If the capacitor cannot hold the voltage properly, this droop rate would be higher than the one we are seeing here, and this is calculated using ddt of Vc, the rate of change of the voltage across the capacitor, and it can also be calculated by Id divided by C. Id is the droop current or the leakage current, right? The leakage current from capacitor, somehow the current is leaking, there will be some discharge, and because of that we are going to get some droop here. Okay, so this is all about the sampling. Now we have two more steps, quantization and then encoding. So these are quite simple to understand. What we are doing, previously after sampling we have discretized the time domain, and now still after that we have the voltage or amplitude domain in continuous state. So in what we are going to do, we are going to discretize that amplitude. Like for this example, we can see that if we have an analog signal which is varying from 0 volt up to 10 volt, so minimum value is 0 volt and the maximum value is 10 volt. If we decide to separate these voltages into 8 different discretized or quantized states, then for each of the states we will have 1.25 volt, right? 1.25 multiplied with 8 is equal to 10 volt. So this is what we have done. We have divided the overall voltages we have starting from minimum to maximum, divided those into 8 different states, and for each of the states we have assigned a kind of state value. So state 0, state 1 up to state 7, 8 different states we have quantized or discretized the amplitude domain. Now this is just for quantization, right? So there will be some terminologies we have to learn for this quantization, and one of the thing is called the number of quantization levels. Like we had 8 states, this will be actually the number of quantization level, which is denoted by L, and which will be equal to 2 to the power n. N is the number of bits in AD converter. So whenever we will be talking about encoders, then maybe we will again understand even more about the capital N. But here you see the L value is relating to the value of capital N in this manner, right? So that means, for an example, if we have a 3-bit analog to digital converter, then the value of L, the number of states we can have, number of quantization level we can have, will be 2 to the power 3 or equal to 8. So if we can increase the number of bit level for our ADC, that means we can have higher amount of quantization levels, and that will increase the resolution or accuracy of our ADC, right? So this is also relating to the quantization step size. So you see the quantization step size, which is denoted by Q, is the smallest change in analog input that results in a 1 level change in the digital output. So basically we are just getting the difference between the maximum value and minimum value, then dividing that with the number of states we want, the number of quantization levels, which is 8 for the case if we take Vmax is equal to 10 and Vmin is equal to 0 volt, and for 8 different quantization levels, the Q value or the quantization step size should be 1.25 volt. Okay, so you can see if this value can be reduced, that will increase the accuracy of our analog to digital converter, right? But this will also take more memory for our system. So there will be some trade-off, how much memory we want to use or can use, and how much accuracy we want. Okay, let us finally talk about encoding. Previously we discussed about that, but here you see the similar example. We have 0 to 10 volt amplitude possibilities we have divided into 8 different quantization levels, and this is shown here, right? And now what we are going to do, because we transmit everything in terms of digital data, which is either 0 volt or 5 volt or 0 state or 1 state, so we will define or assign each of the output states into a equivalent binary value. So for the case, like, this is the formula that will relate to the number of quantization level with the number of bits we require to represent each of the states. So for the case of, let's say in this case we have 8 different states. That means to represent each of them, after putting to this value, we will see that n, the capital N, should be equal to 3 bits per sample. So this is what we have done. Because we have 0 to 7, 8 different states, we can count from 000 up to 111. This is 8 different states, and it will represent the number of states we have into a specific binary code. Okay. And also another thing I should mention, how for each of the states different binary codes will be assigned. There are different methodologies, how different optimizations done in this particular domain, but we are not going to go into details of that. Just understand that the definition of encoding is that we are just trying to assign some binary codes to each of the quantization states or output states we have, right? Okay, now we will look into some types of ADCs that are actually being implemented and manufactured in our everyday life as analog to digital converter. So some of them are flash ADC, then successive approximation ADC. There is another one, dual slope ADC, and finally delta sigma ADC. Here the first three we will try to discuss in our lecture today, and also to understand dual slope ADC we will discuss about single slope ADC, but practically single slopes are not implemented because dual slope is basically an improvement of that, and we will try to understand that. Okay, so let us first start with flash ADC. So I think just by looking at this particular figure, which is a flash ADC, we will understand a lot about how this circuit works. So what you need to understand is, first of all, here we are providing the analog input voltage that can change with respect to time. It can have continuous values, right? And also it should have a sample and hold circuit here, just like before. Even though it's not showing here, you show that. Okay, and there will be a reference voltage VR, which will give us the quantization step size Q right here. So for example, we can take 10 volt as reference voltage for this case, so that I can explain here. And as you can see, we have 8 different resistors here of same value, right? So that means if I have provided 10 volt here, it will be equally divided, the voltage will be equally divided here into each of the resistors, right? So for each of the cases, we will see each of the resistors are dropping 1.25 volt, right? So that means here through this path we are going to get what, 8.75 volt, right? And then after this resistor we are going to get what, 7.5 volt, and then here 6.25, then here 5 volt, and then here 3.75, here it should be 2.5 volt, because the value is 10 volt, right? So 0.875 multiplied with 10 is equal to 8.75. so in this way we have found out. So finally 1.25, and all of the values we are seeing here, this is connected with one of the op-amps in its negative input pin, right? And the other pin, the positive pins of all of the op-amps, the 8 op-amps we have, are connected with the sample and hold output of the analog signal, right? So if this is the case, what should be the output here? Okay, to understand that, let us understand how a op-amp works in comparator mode, right? So whenever we have an op-amp like that, and we have this positive pin, negative pin, and we have these ports, right? And what happens whenever we have two different voltages given here, right? So let's say we have given 5 volt here and we have given 3 volt here, okay? And based on that we are going to get some output V out, right? So how that is decided is based on the supply voltages we have given to our op-amp. So there will be some plus VCC given, let us give that to 5 volt, and there will be some minus VCC, let us keep that to 0 volt. So basically what happens, this op-amp works in this particular formula, okay, based on this formula, which is V out should be equal to A V plus minus V minus. Okay, V plus is basically this one, okay, the positive input pin, and this is V minus. So that means whenever we will have a higher value in positive pin compared to negative, this value will be positive, and this value is actually the amplification factor here. And generally for our op-amp this value is quite high, like 10 to the power 6 or something. So that means there should be a very high value coming to the output, but our op-amp has a possibility of maximum voltage to be shown at the output as 5 volt, because we have provided 5 volt as VCC, positive VCC. And similar thing, if this value is, let's say, what, maybe 2 volt and this is 3 volt, now the negative pin has a higher voltage compared to the positive one, then this difference should be negative, and with a multiplication factor like that we should get a very high negative value. Again, that will get saturated to the negative value we have provided here, which is 0 volt. That means at the output we are going to get 0 volt. So this is how op-amp can work as a comparator. So we are just comparing the two voltage we have provided as the input, and based on that either two of the situations will happen. So either we are going to get 5 volt at the output if the positive pin has a higher voltage compared to the negative one, and if this value, the negative value, is higher than the positive one, we are going to get the value of 0 volt. So the two possible states. So this will kind of work like a digital device which can only pass two values at the output, high or low, right? So using these two, using these pins here, output pins, we are going to get either 5 volt and 0 volt, and this will be connected with a priority encoder, right? And let us try to understand from the values we are getting how priority encoder can output the designated or corresponding digital value, right? To understand that, let us look at this example of a 823 priority encoder. Before understanding priority encoder, let us first understand what an encoder does. Just like your encoding we learned about in ADC conversion process, what we are doing, we had 8 different states. After quantization, we assigned a specific 3-bit binary value for each of the cases. Same thing is happening here. So for each of the inputs we are providing, we can have a specific 3-bit output value, right? So for, let's say, for D0, if D0 is 1, all the other values are 0, then the output should be 0 0 0. If D1 is 1, all the other input pins are 0, that means output should be 0 0 1. So in this way, we are encoding the 8 different input states into 3-bit binary values, right? Now obviously it can work, but there will be a problem if, let's say, we have a situation that in D2 we have given logic high, in D5 we have given logic high, and for all the other input pins we have given logic 0. Then we have two possible input pins getting high voltage, and at the output what should happen, which one to actually be transmitted as the signal, right? So both of them will actually interfere with each other. That is the problem. So because of that, we have to give some kind of priority to the input pins, so that if 2 or more pins are getting high voltage at the input, which one to be prioritized. So this is done using this kind of priority encoder. So that means you see here D7 is getting the highest priority and D0 is getting the lowest priority. So that means if for this case, this particular case, because D2 is getting 1 and D5 is getting 1, all the others are getting 0. In this case, D5 will get higher priority and the output will be 1 0 1. So in this way, so this is what we are seeing here. The X means don't care. So whenever D7 is equal to 1, we don't have to worry about all the other inputs, whether they are 1 or 0, doesn't matter. We are going to get the corresponding encoded output, which corresponds to D7, right, which is 111. So in this way it works. So that means here also what we are going to see, the outputs of the op-amps, we can see multiple op-amps can output logic high at the same time. In that case, this priority will help us, right? So let us say we will just try to understand using some example. Let's say we have provided an analog input voltage which is 5.5 volt. So if 5.5 volt is given, which is coming to the positive pins of all the op-amps, for all the op-amps what should be the output value? So we will see that for the first op-amp here, positive pin is getting 5.5 volt, negative pin is getting 8.75 volt, negative is higher than positive, that means the output should be 0 volt, right? And for the next one, 7.5 is higher than the one as input, 5.5, so the output should be 0. Here 6.25 is higher than 5.5, so output should be 0. Here you see for this one 5 is less than 5.5, that means the value should be 5 volt, or logic 1 you can say. Here also what should happen, positive is higher than the negative one, so 5 volt or logic 1. So for all of them now we are going to get logic high or 5 volt. If that is the case, you see we have I4, I3, I2, I1, all of them getting logic 1, and I0 is by default will be taking logic 1, because initially if nothing is happening, the output digital value should be 0 0 0, right? So if this is the case, you see I4 will get the highest priority compared to all of the ones we have here. For I4 the corresponding digital output should be 1 0 0, right, according to the truth table we have. For D4 you see the output is 100. So in this way we can understand. So 100 is the digital output that corresponds to the analog input we have provided 5.5 volt. So in this way this flash ADC works. I think it's quite easy to understand. Yeah, so what are the benefits and disadvantages of this kind of ADC? Obviously you can understand it will be very fast. Parallelly all the op-amps are working, so instantaneously we are going to get the output, and simple to understand, simple to implement. And you see speed is only limited by the gate and comparator proportional delay, so very fast obviously. But the problem is it will be very expensive. Each additional bit of resolution will require twice the comparator. So that means if I want to get a ADC, flash ADC that has 4-bit digital output, that means instead of this 8 op-amp we should have 16 different op-amps and 16 different resistors with equal value, so that we can get 16 different situations here for comparison. So that is the problem. As we increase the number of bits, exponentially the number of op-amps required and number of resistors required will be increasing, right? So that is one of the drawbacks of this kind of ADC. Next we will learn about successive approximation ADC. So to understand that, first of all let us briefly understand the components of this ADC. The heart of this system is a thing called successive approximation resistor. There is also some control logics built into that will control the whole circuit itself. There is also another digital to analog converter inside of this analog to digital converter, which helps us or helps this circuit to operate properly. So this ACR will output different digital values, so that will be coming to this digital to analog converter, and that will convert that digital value into its analog representation, right? That will be going through this comparator into its negative input pin, and the analog signal we want to convert to its digital signal is the V-in we will provide through this pin, which will be going to a sample and hold circuit, and the output of that will be connected to the positive pin of this comparator. So based on that, there will be some comparison happening here, and the output of that will be going through the ACR. There will be some control logic inside of that. So based on this comparator value, ACR will decide what to do next. Okay, so now the first thing we need to understand for this device is that this device works in an iterative process, kind of like a guessing game. So each time the ACR will try to guess the possible corresponding digital value of the analog input we have provided, and it will try to evaluate its guess based on this comparator, and it will get some feedback, and based on that it will try to improve its result step by step iteratively. Okay, to understand that, let us try to look at the input output relation of this digital to analog converter. So for our case, we will try to always look at an example of 3-bit ADC which contains a 3-bit DAC, right? The input output behavior or relationship of that DAC looks something like that. So you see here we are seeing this kind of 3-bit input to the DAC, and corresponding output will be coming, and the relationship is such that you see for each of the cases, because for this particular case, let's say we are just taking such situation that the reference voltage we are providing here is 10 volt. If reference voltage is provided as 10 volt, then the corresponding analog outputs will be such like this. Okay, so you see each of the states have 1.25 volt increment, right? So 0, then 1.25 up to 8.75 volt. So here you have to understand for quantization we looked at states such that it is containing a voltage range starting from, let's say for this case it was 8.75 volt to 10 volt. This was 7.5 volt to 8.75 volt. So these are just conceptual understanding. In practical situations it is not exactly like that, but we can avoid those complications here also. Just to understand here, you can understand that for this particular digital input, the DAC outputs this value, which will be a specific value, because with this pin, the output pin, we cannot output a range of values like we had for quantization, or for the case of ADCs we saw, right? It was 8.75 volt to 10 volt, this amount of voltage range. But here, because we are just getting one voltage, that will be a specific voltage like that, each of them 1.25 volt higher than the other one. So if we understand that, time and time again we will try to return here to get the corresponding analog output of the digital values, right? Now to understand the intuition of this device, how iteratively we can guess a value, let us look at this particular graph here. Okay, so let us think of a situation where our 3-bit ADC has got input signal, the analog signal, as 6.5 volt. Okay, for this case what happens? We know that we have to guess each time, and we have to evaluate our guess, right? And in this way iteratively we will try to improve our result. So let us say we started with 100, because we will start from the most significant bit, then one by one we will look at the lower bits as well. So first of all we have kept the most significant bit as 1, then 0, then 0, and we will try to evaluate this value with the analog voltage that is provided as input, right? So this value will be guessed by ACR, successive approximation register. It will be sent to our DAC. DAC will convert that value into its analog value, and this is that table that will show us what will be the corresponding analog value from the DAC. So for 100, the corresponding analog value is 5 volt, right? So if 5 volt is coming from there, then we will try to evaluate our guess, right, which is 5 volt. So obviously 6.5 volt is higher than 5 volt. So if that is the case, try to understand that obviously it will be these three, the possible values for our analog signal can be these three, obviously not these three, right, these four. So that means the most significant bit must be 1. It cannot be 0, because if they are 0, then these will be the guesses and these are not correct, these are lower than the ones we have guessed, we have to increase our value of the one we have guessed, right? So that means what we can do, we can keep the most significant bit as 1 and move on to the next one, which was 0. Now what we'll do, because the input voltage was greater than the one we have guessed, now we will start with this one again, continue with this one. So 1 1 0, this is the one. So this is the value guessed by SAR now in the second step, and this will be sent to our DAC, right? So if that is the case, for this one 1 1 0, we know the corresponding value is this one, right? 7.5 volt is the corresponding analog value, and that will be compared with the original input signal, and we know 7.5 is greater than 6.5. that means now we have to guess a slightly less value, not higher than the one we have guessed. So our guess is not quite correct. The next bit 1 should not be, the middle bit should not be 1, it should be less than that, right? So that's why we will go on to this path here, because the input voltage is less than the one we have guessed, and now we will come here. So we have to keep the second bit as 0, and we will start with the third one. Again, for the third bit, the least significant bit, we have guessed the value as 1, and this is the corresponding value 101. And now for this one, the corresponding analog value is what? 101, this one 6.25, right? 6.25 we have to compare with the input signal. So now again 6.5 is greater than 6.25, so that means our guess is kind of correct, right? Because the value is higher than that, it can never be lower than that. So the last bit, the least significant bit, should be 1, it cannot be 0. Then if this is 0, then it will be much lower than the value we have at the input, right? So we have now guessed for all the 3 bits in 3 steps, from here to here to here. So finally the value we have guessed, the closest possible digital representation of our analog signal should be 101. So in this way, because we have 3 bits, we have to iteratively in 3 steps have to guess the corresponding digital value of our analog signal. So in this way, briefly, I think you have understood this is the way this particular device works iteratively. So now let us repeat our discussion with an actual example here of a 3-bit successive approximation ADC. So here you can see the V input here is given as 3.2 volt and reference voltage here is 10 volt. For this case, obviously we are going to follow this table for the digital to analog converter, this one, right? This one will be giving this kind of output. So let us understand how in 3 steps this process will complete, right? So everything will start with this start signal here that will be coming to the SAR, and SAR will do what? It will start its guessing from this value. D2 is equal to 1, D1 is equal to 0, D0 will be equal to 0. So the input to our DAC will be 100, and DAC will output its corresponding analog value, which is what? For 100, the corresponding analog value is 5 volt. So that is we are getting, and this value here will be compared with the analog voltage we have provided. So we have provided 3.2 volt that will be going through the simple on hold circuit, and this will be compared. Now 5 volt, our guessed value is obviously higher than 3.2 volt. That means at the output we are going to get a logic low, right? So logic low means this signal will be going through our SAR, and SAR will understand, because our guessed value is higher than the one coming from the input, we have to guess a value that is less than the one we have guessed. So that's why we have to clear the one we have guessed. 1 should be 0. The most significant bit was guessed as 1, it should be 0. So we will be D2 will be cleared to 0, and at this stage the resulting bit pattern should be like this at this start. And then we will start the next step, which is what? We have to keep the next significant bit, which is the second one, to 1, and send this value to our deck, right? So the corresponding bit value is 0 1 0, and it will be sent to the deck, and deck will output the equivalent analog voltage, right? So from the table we know that for 0 1 0 the corresponding analog value is 2.5 volt. So basically here we are going to get 2.5 volt in the negative pin, and the analog input voltage is 3.2 volt, just like before. So now positive pin will have higher voltage compared to the negative one, so we are going to get a high pulse here. High pulse here means SAR will understand whatever we have guessed for this particular bit is correct, we can keep it at that value. So our guess was 0 1 0, we can keep it to this value. The after second step the resulting bit pattern is 0 1 0. So we will start with the third step. In the third step, what we will do, we will try to modify the least significant bit D0. We will keep it at 1, so the corresponding bit pattern is 0 1 1. And for that, what is the corresponding analog value? For 0 1 1, this is 3.75 volt, right? So the deck will output here 3.75 volt, and for 3.75 volt is coming here, 3.2 volt is coming from the input. Now negative pin is at a higher voltage compared to the positive pin, right? So the signal will be low coming from the comparator, and that will be going through the SAR. SAR will understand for the third bit whatever we have guessed this is not correct, we should clear the last bit to 0, so that will be cleared to 0, and the resulting bit pattern will be 0 1 0. This is the closest digital representation of the analog signal V in we have provided, which is 3.2 volt. So this is the output, and at this point after 3 steps is completed, SAR will understand our process is complete. It will transmit a EOC signal, which is end of conversion signal. Okay, so end of conversion signal, we will it will let us understand that we can stop here, and whatever signal we are getting from the output of SAR, this is the actual representation of the analog signal we have provided. Okay, now we will try to learn about single slope ADC. Because we need to understand about dual slope ADC, initially we will start with single slope ADC, and we will look at what are the shortcomings of this type of ADC, and then how these are improved in dual slope ADC. We will try to understand. Okay, so this is the circuit of single slope ADC, and one by one we will try to understand how each of the components of this device works, how that helps. And we will start with this RAM generator first. Okay, what's the purpose of this one and how it is built? So RAM generator basically means, this is the graph you can see. With respect to time, the voltage is increasing with a positive slope, right? So this is the output of a RAM generator, and the circuit we use for this kind of RAM generation, let us try to understand that. Okay, so we all know about op-amps, and we will try to look at one of the configurations of op-amp here. So this circuit basically outputs a ramp signal. So let us try to find out the current going through this path and this path. This one should be what? The voltage here minus the voltage here divided by the resistance. So Vref minus 0 divided by R should be equal to this current, right? So this current is basically what? Current through the capacitor can be written as IC is equal to C dV by dt. So here the voltage is basically the voltage difference between the two plates of the capacitor. So in these two terminals, what is the voltage difference that we have to calculate to find the value of V here? So we can write what? C d dt of 0 minus VR, that is the voltage difference between these 2 points, right? So this is the final equation, and finally we can say what? V ref divided by R equals to minus C dVR divided by T. Now what we are trying to do is find out the value of VR, so we will try to keep VR in one side and try to move everything in the other side. So for that case, we can also put the C here, so minus V ref divided by RC equals to d dt of VR, right? So that means what we can do, because the differentiation of VR is equal to this value, we can also say integration of this value should be equal to VR. So VR should be equal to what? Minus 1 by RC, because these are constant, we can keep it outside, and integration of 0 to T should be V ref into dt. So this is the final formula for our output voltage of this device, right? So this is an integrator, and you can understand if you try to solve that, the output value should be what? VR should be equal to V ref into T divided by RC. This is the final value we are going to get, right? So if V ref and RC, these things are constant, then we can say VR is proportional to T. So as the time progresses, VR will increase, so kind of like a positive slope, right? So we are going to get a graph like that, where with respect to T, our voltage, the output is increasing in this manner, and the slope of this increase will be equal to what? Minus V ref divided by RC. So you understand, one of the issue with this thing is we have gotten the slope as negative, right? So it should be something like that, maybe here, something like that. So starting from 0, it should be negative, but in this graph we are plotting a positive slope ramp, so we need to omit or eliminate this negative sign somehow. So what can we do? We can just initially take the input voltage as minus Vref, so that after all the calculation we can omit this negative sign, and we are going to get the slope as what? Slope as positive Vref divided by RC. So this is the circuit, and from that we are going to get this signal, ramp signal, which will be going to this circuit, right? Here you can see in this circuit we have Vref, so there should be actually minus Vref, right? So we can keep it at minus Vref, and that signal will be coming to the ramp generator. Ramp generator will generate a ramp signal which will start from 0, and incrementally it will increase its value with a positive slope, right? And that will be coming to the negative pin of the comparator, right? And we obviously, because this is an analog to digital converter, we need to have an analog signal coming through this pin, which will go to the positive pin of analog input. Now this comparator here, this comparator will actually works like previous cases we discussed. So a positive VCC of 5 volt or logic high will be given to the plus VCC, and negative VCC or minus VCC will be connected with ground. That means whenever negative pin will be higher than the positive one, we are going to get a logic low here, and whenever positive sign positive input is higher than the negative input, we are going to get a high signal or 5 volt, right? That will be going through this path. Okay, so next let us look about this AND gate. We know that when we have two pins, such like one of the pins is giving 0 voltage or logic low here, whatever you transmit through the other pin should not pass the gate, right? For the AND gate, this is the case. So if from the comparator logic low is coming if you transmit any kind of clock signal that will not be passing through this path. And whenever we have a high signal, the signal you are providing from this clock will transmit or pass through this gate. That is the idea. So this is kind of like a case where either we are going to allow the clock signal to pass or not pass, right? And if that is allowed, this clock signal will always generate. This is always continually be generating a clock signal, kind of like that. So even though this is not properly shown accurately, maybe there can be 50% duty cycle like that. So something like this, okay? This kind of clock signals will be coming from this path, and the high voltage is 5 volt and the low voltage is 0 volt. In this way, the duration here and here can be same. Low voltage and high voltage, this is the total time period of that signal, the clock pulse. We can call that TCLK or T clock. So this is the time period of one cycle of the clock pulse. We are going to use this value later on, so remember that. Okay, so now what happens to the counter if clock pulses are going through the counter? That is the question, right? So if you remember from your previous semester, counter basically works such that if we have a counter like this, let us say we have a 3-bit counter, 3-bit counter, and here we have this clock pulse, and the output of that counter should be 3 bits, right? So we can also have a reset button here if we want, right? So now whenever it starts, if we have a clock pulse like that, let's say one clock pulse like that happens, then from initial moment, initial value is 000 for this counter, and whenever we get one clock pulse here, it will increment its value to 001. Okay, so it will be 001. Then again, if we get another clock pulse here, it will increment its value again to 010. So in this way, it will increment its value each time we get a clock pulse through the clock pin, and it will count up to what? It will count up to 111, the maximum possible value for a 3-bit counter. And then again, if you give a clock pulse again, it will reset to its, not reset, but it will again come to the lowest value, which is 000. In this way, it will continually be counting each time you are giving a clock pulse. And also you can reset that. If you press the reset button, everything will be going to 000 state, right? In this way it works. So we understood what is the functionality of counter here. And also you will see that the counter is connected with some kind of latches. Latch basically means that whatever signal is coming here, that can be stored if needed by giving a high pulse through the enable pin. Then whatever signal you are providing here, that is temporary, it can change, but if you give the enable signal, these particular values coming from the input will be stored here for indefinite time until you reset them. Okay, so you will see that the digital output then is showing the value we have given at the input. Then after that, if the values are changing at the input, still because the previous values are stored in the latches, that will be showing up through the outputs. Okay, so that is the purpose of latch. Okay, and finally let us talk about control logic. So this is the heart of this particular device. So in different situations, it will get, based on getting different signals, it can control different devices. Like you can see, it can either clear the counter, and also it can enable the latch, it can reset the RAM generator. So it is also doing this kind of things based on the logic it is getting from the output of comparator. So output can be low or high from the comparator coming through the control logic. Based on that, it will change the signals here in these 3 paths to control the other devices. That is the basic idea. So as we have learned about the functionalities of all the components, now we can start how it works. Okay, so we know that this RAM generator can increase its voltage starting from 0. Incrementally it will, with a positive slope, it will increase its value. So something like that. So the whole device starts working through the signal of control logic. Okay, so when initially starts, control logic will send a signal here to clear the counter, so that if there is any garbage value stored, that will be cleared here to make it 0 0 0 0 0 0 in this state, the initial state. And then it will also reset the RAM generator, so that if in the RAM generator some voltage is already stored because of the previous process, it can be reset to 0 value. And then what happens, then we can start our process. Some analog voltage or analog input Vi will be given through analog input, the positive pin. And also, because we have started the process, RAM generator will start to increase its value. So this is what we are seeing in these graphs. You see, starting from 0 value, maybe the voltage at the output of RAM generator is gradually increasing as the time is progressing, right? But we can safely assume that initially, whenever this process is starting, the input analog voltage is higher than the RAM voltage, because here in this graph we can understand this is the signal, input signal or Vi coming from this pin, and as the RAM generator has started its process, it will start from 0 voltage and gradually increase its value. But if you compare these two, initially still Vi is at a higher voltage compared to VR. VR is this one actually. Okay, so VR is the output coming here and Vi is this one. So obviously we can say that this positive pin is getting a higher voltage compared to the negative one. As a result, at the output of this comparator we are going to get a high signal, logic high, and that will be coming to this AND gate. Because if this is high, whatever clock pulse is getting here will be going out of the output, right, of the AND gate, right? So it will be passing through this gate and reaching this counter. If clock pulse is reaching the counter will start incrementing its value, right? Starting from 0 0 0 0 0, it will start incrementing value to 1 2 3 in this way. In binary values it will try to increase its value. So it will continue, this counting will continue as long as this clock pulse is persisting or it is available here. Obviously these clock pulses will be there, and as a result this counter will increment its value one by one. It will gradually increase its value. It will happen, but for how much duration, that is the question, right? So it will stop, basically it will keep happening, but at certain point it will stop whenever this VR voltage, the RAM voltage, after increasing, it will at one moment obviously be equal to the analog input voltage, right? So we are seeing this in this graph in this moment, right? So here you can see, maybe I can use another color here. Maybe you can see here the output of the RAM voltage VR is exactly equal to the input voltage. At that moment what will happen, just after that this minus pin from this VR will get slightly higher voltage compared to Vi, and as a result now at the output of the comparator we are going to get a low signal. Because of that, now because it is getting low signal, the clock pulse that was passing through the gate will not pass anymore. There will be no clock pulse coming through this counter, right? And because of that, counter will suddenly stop counting or incrementing its value. Okay, so whatever it has counted up to this moment, it will keep it at that and it will not increment anymore, right? So that is the moment. This is the moment when we will stop. And because one thing you have to understand, this comparator signal is also coming to the control logic. Now control logic, previously it was getting high signal, now it's getting low signal. As a result, now it will understand, now I have to do something. I have to, my process is complete. Our counter has counted up to how much it should count, and it will actually say that the signal the digital output coming from the counter is the equivalent digital representation of the analog signal we have provided. It will understand that, and because of that, what it will do, first of all, it will enable this pin here, giving it a high signal here to the latches, so that whatever signal that is available to the counter will be stored into the latches and coming out of the digital output. This is our corresponding digital output that we should get for the VI we have provided. Okay, and also after that, what it will do, it will try to clear the counter, because our process is complete. Now counter can be reset to its initial position, and also a reset signal will be going to the RAM generator, so that whatever voltage that was stored, because there will be some stored voltage, because it is incrementing its value, it was incrementing its value, so it has to be reset to its initial position again to 0 voltage. So that will be done and our process is complete. So whatever digital signal we are getting here through the counting process, this will be the digital equivalent of the analog signal we have provided. Now the question is, how can we confidently say that the signal we have got here, the digital signal we have got here, this is the correct representation of the analog signal we have provided here? How can we prove that? To prove that, try to understand that previously we learned about one of the equations here. If you remember here, VR was Vref multiplied with T divided by RC1, or we had come from here. Because we have provided minus sign here, we can also omit the minus sign here, but let us try to write the equation again. Okay, so it was something like that. VR is equal to, I am not giving the minus sign, so 1 by RC integration of T 0 and Vref. We can actually put minus here and minus here, that will be easier to understand maybe, and here we should have dt. Now the thing is, we will try to calculate the amount of voltage we have accumulated during this t1 time. So we can put this to t1, right? So we can also write, this is not actually VR, it can be said that VR t1, VR during t1. So let us say VR, maybe I can write something like that, VR t1, this is the value, right? We can also omit the two negative signs and also put Vref outside. So if you integrate this thing, you are going to get what? T1 here. So this is the final equation we have for VR during T1, VR after the duration of T1. And after the duration of T1, what happens? VR becomes equal to VI. This voltage becomes equal to this voltage. So we can also say this voltage is equal to VI. So if that is the case, from this one we can get some idea about whether the signal, the digital signal we have got as the output, whether this is actually equal to the analog voltage or not. So for that, again we are going to do another thing, that is let us try to represent T1 in another way, which is T1 is this duration. We can also say, we know that this clock pulses here, we said that this clock pulses we got the time period of each of the clock pulse, we said that it was T clock, right? So we can say, if after this whole T1 duration we have counted up to n, or we have counted n times, okay, starting from 0 0 0 whatever initial value was, after each clock pulse we have incremented our value in the counter by 1. So in this way we have counted for n times, and we can also say we have counted up to n. So let's say if I have counted for 14 times, obviously we have counted up to 14 starting from 0 0 0 0, then we have done that. So this is that n value, and for each of the counting process we had to endure t clock amount of time, because after this amount of time one increment was happening in the counter. So the total duration of time during which we have counted is equal to T1, which can also be represented in terms of n multiplied with TCLK, right? So we can put this value here. That means what? Vi should be equals to V ref T1 is equal to N multiplied with TCLK divided by RC. So this is the final equation we have got, which represents the whole relationship between analog value and digital value, right? So here we can say Vi proportional to N, because Vref is a constant which is given by us, T clock is a constant given by us, which is the basically the behavior of what behavior of our clock pulse, the time period of our clock pulse, and R and C is the resistor and capacitor of our ramp generator. This is also constant. So all of the values are constant. We can say Vi, the input analog voltage, is proportional to the number we have counted up to. Okay, or we can also say the time, the number of times we have counted, incremented in our counter. So obviously this value is representing our digital value, because based on that we are going to get the digital output, which will be equal to the analog input we have provided. So we can prove, or we have proved, that the signal we are going to get here as digital output will be equivalent of the analog input we have provided. Okay, now the question is, what are the limitations of this device? One of the issue is, you know that if I want to represent this equation in another way, maybe we can do that. Yeah, here we can do what? We can keep N here and everything in the other side, then Vi multiplied with what? RC. At the bottom we will have Vref multiplied with TCLK. We can remove that. Okay, yeah, this is the equation we have. So you see, one of the issue is the number we have counted up to, the value of N is actually dependent upon the value of R and C. So let's say if in our device, if there is any kind of environmental effect because of temperature or something, the value of capacitance or resistance can be affected, and that can affect the value we have counted up to, which is the digital output basically. So obviously based on that, there can be noises effect like that can happen. So this is one of the limitations of this particular device, single slope ADC. Somehow if we can eliminate the effect of this RC from this equation, then obviously it will be a better device, you know. So that is what we are going to try in the next device, dual slope ADC. In the dual slope ADC we will see, whenever we get this kind of equation, there will be no RC. That means RC, the value of resistance or capacitance of the ramp generator, will not affect the digital output. Okay, okay, so now based on the limitations we have discussed in the previous ADC, single slope ADC, we will try to improve on that using this device called dual slope ADC. So process is kind of similar in this case like single slope, but here we will see that we have to complete the whole process in 2 steps. So there will be 2 types of ramp generation, as you can see here, and after that we will get the digital output here. Okay, so again here try to understand how each of the things work. First of all, you see here we have 2 inputs here. This is the analog voltage we want to convert to digital version. So this is the input we will provide here, but you see there's a negative sign here. That means we will basically are trying to get the basically we have just inversed the polarity right here. So this will help us. We will understand how that helps. Like just like before we had minus Vref in the previous case, just to omit that negative sign we are using this type of behavior, right? And another thing is your reference voltage. So here this one is, this arrow sign basically means this is a switch. So this switch can be either connected to this input voltage here or with the reference voltage here, and this switch can be controlled through this switch path, which will be controlled by this control logic, right? So we will see that in some of the cases the switch is connected with input voltage that will control this particular circuit. If you remember this circuit from your previous ADC example, this is just a op-amp integrator, right? So it will work as a ramp generator, and this ramp generator will be controlled in some of the cases by this input voltage and in some of the cases by this reference voltage. Okay, based on that we are going to get a VB voltage here. This will be compared with this ground. So based on that, sometimes you are going to get low signal or high signal here, and that will control the control logic. So based on that, we are going to see that in some of the cases this clock pulse is getting passed here, and some of the cases this is being prohibited and it is not going here for helping this counter to count up, right? So as long as there is a as long as there is a clock pulse here, the counter can count incrementally count to a higher value, and also there is a pin here called overflow. So what is that? So you know, each of the counters we have a maximum value up to which it can count. Like for 3-bit counter, that maximum value is 111. So that means whenever we reach that maximum value, that is the overflow for that counter, and it can sense that, the counter can sense that it has reached its maximum value. At that point, what it will do, it will send a signal, a overflow signal to the control logic, so that control logic can make some decisions and send some signal based on that situation, right? So these are the things, and clock pulse will always be here coming, just like in the previous case, always will be generating, but whether that will be passed through this counter or not will be decided upon the value of VC. Okay, and also sometimes overflow, this kind of, okay, we will see, but briefly you can understand how each of the components of this device works. So let us start. Like if you remember from your previous example, you know that we can have an equation like that. So VB, we can say VB because this is the output of this ramp generator, right? VB should be equal to what? Minus 1 divided by RC, 0 up to T, and integration of whatever signal we have provided. For example, if we have V in, so we can say minus V in dt, right? So this is for the case whenever we have switch is coming here, and based on that we can also simplify that. Maybe we can simplify that later on, but yeah, let us try to understand what happens initially whenever the circuit initiates. So we will have this voltage and this voltage coming here. This is the input voltage, right? And everything will be in reset condition, so there will be no charge stored in the capacitor, so VB will be initially 0, just like here. You see in this graph with respect to time, how the voltage VB is changing, we can see that. So initially the voltage VB is 0 and the counter is reset, that means it is starting at 0000 condition, and at initial condition control logic will send a signal through this switch control such that this switch is connected with minus V in, right? So for that condition we are getting this kind of equation, right? So, and we will see that at this condition what happens, because this minus V in is connected here and this is controlling this particular circuit here, this ramp generator here. The output should be something like that, V in multiplied with T divided by RC, right? So with respect to time, starting from 0, this VB value will gradually increase like that. Okay, so gradually it will increase like that, and we are going to see that the value of VB is increasing here, and after this comparison obviously the negative pin will be at a higher voltage compared to this positive pin. As a result, this is a comparator with possible values 5 volt and 0, so we are going to get what? A logic low, 0 voltage here, right? So if there is 0 voltage, what happens is this control logic understand that the clock pulse that is coming from here should be passing through control logic and going to the counter. Okay, so it will help the counter to count up. So after each clock pulse, counter will increment its value, so it will gradually increment and this will continue, right, up to which moment, right? That is the question. So it will keep continuing up until it reaches its maximum value. Okay, the counter, if let's say, as I said earlier, if the counter is 3-bit, that means 111 is the maximum value it can count up to. It will reach that value and it will understand it is in overflow condition, right? So that moment is basically in this graph, this moment. Okay, so basically starting from 0 up to T1, at T1 counter will reach its maximum value, it will reach overflow, and there will be a overflow signal coming from the counter to the control logic, right? So because this signal is going to control logic will understand that now I have to do something based on this situation, and that is what? That is, this switch control will send a signal so that this switch position is changed to here. Now something like that will be connected to VREF now, and also because this counter has counted up to its maximum value when overflow happens, after that again it will start from its initial value. It will kind of like resetting, right? So after this T1, this counter will again start from 0000, that initial value again. Okay, let us try to resolve this situation. So we said that for this condition, whenever we have minus V in connected, from 0 up to T1 we had minus V in connected here through the switch, and we can modify this equation like that, right? So this is that, and actually we can call that VB max. So within this duration we have reached here, let us call that VB max, right? So let us call that VB max maybe, right? So what will happen now, because we have changed the position of switch to VREF, and because we have a positive sign here, we had negative sign here, because of that we had a positive slope for the first condition, and the voltage was increasing and up to VB max value. Now what will happen, because we have a positive sign here, from here it will gradually decrease its value, or VB will gradually decrease, right? And it will keep doing that up until it reaches 0 value. So whenever we have VB is equal to 0 value and crosses that value, maybe it can go to negative value also. So at that moment we are going to see that positive pin is again at a higher voltage compared to VB, and it will become what? This 0 will become 1. So there will be a high signal coming to the VC, and based on that VC will understand that the overall process is complete, our conversion is complete, and this clock will now not be passing through this control logic through this counter will stop its counting, and whatever digital output we have got, that will be the final digital output of the corresponding analog data we have provided at the input, right? And so based on that everything will stop basically, and our conversion is complete. So we will try to understand how this digital output is actually the equivalent value of this analog data. That we will try to do that, but let us try to understand for in this duration what happens actually in this duration. I mean from T1 to T1 plus T2, or actually this duration means T2, right? This is T2 and this portion is T1, right? Now during this duration, if I want to get the integration of how much voltage we are actually changing, that can be done in this way. So it's same kind of integration, but here we will have VREF, right? So let us call that what? Just for example, let us call that VB2. Okay, so in this condition we are going to have a minus sign again, but the limit should be different. So T1 plus T2, and at the bottom it should be T1, because from T1 up to T1 plus T2 we had this process, and there will be some Vref and dt. So this is the overall equation, and here we are going to see that there will be a negative sign. Okay, so this is in this duration, right? So basically we can also equate these two things, this one and this one, because in this duration from 0 to T1 what happens, from 0 up to this VB max we have incremented. So this length here is this one, right? VB max, this length is basically this one, and here what happened, from this VB max we have reached again 0. So again we have come or traveled this length. Okay, so this value is also equal to VB max, right? So we can say that V in multiplied with T1 divided by RC equals to, we can just think about the magnitude, not the polarity. So we can omit this negative sign because both of them are equal to VB max, but the magnitude is opposite. So I mean the polarity is opposite, so we don't have to worry about that. Maybe we can just think about the magnitude. So if that is the case, we can write this, and we can also omit RC from both of the cases, right? Now you can understand that already we have omitted RC from the final equation, so the effect of resistance and capacitance of the RAM generator has eliminated here. So the limitation we had in the previous case, it has been eliminated here. And now we will try to generate a finalized equation for this digital output to prove that the digital output we have got is actually the proper digital representation of the analog signal we have provided, right? For that one we have to represent T1 and T2 in a different way. So how can we do that? Maybe we can just make T1 equals to what? T1 equals to 2 to the power n multiplied with TCLK. Why is that? For n bit counter, the maximum number it can count up to is equal to 2 to the power n, right? Like for example, for a 5 bit counter, the maximum value should be what? 2 to the power 5 is equal to 32. So 32 times it can count. And for each of the counting, it needs a clock pulse which has a duration of t clock, right? Just like before, just like your previous example, the time period of each of the clock pulse is t clock. So T1, from this duration, this to T1, in this duration the counter starts from 0 and counts up to its maximum value. So it is actually 2 to the power n to the power capital N multiplied with TCLK. And for T2 is equal to what? We can call from T1 to T1 plus T2, or in the duration of T2, what we have done, we have counted up to the value of our digital output, right? So let us call that n, just like before. So n is the number of times we have counted, or the value we have counted up to after the reset, after T1, right? After T1 we have reset the counter and we have started again. So from that we have counted up to n, which is the digital output basically, multiplied with, for each time we had to spend t clock amount of time for each of the clock pulse, right? So we can just replace those values here. So V in multiplied with 2 to the power n into t clock equals to v ref multiplied with small n multiplied with tclk. So we can remove the two clock periods here, and finally we get this value, right? And we can say that in the number of times we have counted up to here is equal to v in divided by v ref multiplied with what, 2 to the power n, right? So you see here we can say from this one we can definitely say that n is proportional to v in. The number of times we have counted up to in the t2 duration is proportional to the analog voltage we have provided. So proved that the digital output we have got is actually the proper digital representation of the analog signal we have provided.